Hello, my friends. So, today I'm going to discuss a very important problem, and this is quite a very tough problem and very less chances of it to come in INPHO2 because it is very difficult to think at exam time. So, let us discuss the problem, and it is one of the most toughest problem I will claim that available on YouTube. So, let us discuss this problem. So, the title of the problem is Let's Play Chess, and here goes the problem. A normal 8 cross 8 chessboard is made from plates of two different metals. So we got two different metals of conductivity different, sigma 1 and sigma 2. So they are the only conducting elements in this construction are the two thin terminal strips which are very good, which have very good conductivity. Um so these two terminal strips, as you can see here, of thickness t, this terminal strip is the metal strip that will get us the conductive part of the board, and all these black plates and white plates are the conductive plates. One is of conductivity sigma 1 and one of conductivity sigma 2. So here we have been given the arrangement. The length of the board is L. The length of the board is L, and the voltage across the two sides of the board is V actually. Okay, so let us discuss what we need to find here is the current that passes through the board actually. Okay, so let us discuss how the current streamlines work here and how the potential difference works across the board. So here it says that they are positioned at each end of the board. The common thickness T of the board is much less than the length L of the board. So the conductivity of the light square is sigma 1 and the dark one is sigma 2. Find the current flowing through the chessboard if a steady voltage V. If a steady voltage V is applied uh, across the terminal of the interface, between interface resistance between the squares can be neglected. So we have been given a battery that is connected across the so any interface resistance between the squares can be neglected. So let us discuss the solution, and it is a very conceptual solution and very difficult to be thought at exam time. So let us discuss the solution. Here we have been given if all the squares are of same conductivity. First we will consider the square to be of density conductivity sigma 1, and then we will consider it to be of sigma 2. So if the square is of conductivity sigma 1, we can say that the total current density that is passing through the square is sigma 1 e, that is the current density, and if we just multiply it by the area actually, so we'll get the current. So here we will just do I1 is equal to sigma 1 e L T and E is equal to V by L, so we'll get I1 is equal to sigma 1 VT, and similarly for sigma 2 we will get I2 is equal to sigma 2 VT. So the net current that passes through the net current that passes through the square, that the chessboard, is the geometric mean of the two currents actually. I should say V2 VT root sigma 1 sigma 2, and we will prove this with a very conceptual proof. I have a very conceptual proof here. So geometric mean of two currents, when this is applicable, when this law is applicable, this is applicable only when the two pair of points that we choose, if we choose a pair of point that is A and B on any of the square, whether it be the white square or whether it be the black square, if we choose two pair of points, suppose we choose A comma B, which can be transformed, actually the 2 points can be transformed by rotating the square to 90 degree, such that sigma A into sigma B is independent of the location of the points chosen. So let us discuss what this actually says here is. So sigma n to sigma b should be independent of the points chosen except at the interface. So here we will say that, let us see this uh, 2 cross 2 chessboard. Let us first consider the case of 2 cross 2 chessboard. Here we got white color, here we got black color, here we got black color, and here we got white color. So if I took a red point, suppose if I took a red point and just fix the point, and for all rotations this point lies here. So if I just take the point, and at this point if I write the product of conductivity, it will never be sigma square or sigma 1 square or sigma 2 square. It will always be sigma 1 into sigma 2. So this is the condition that while rotating the color must change. While rotating the square, the color must change. So for A and B, the 2 points that we choose here, they should transform such that they can be transferred into each other by rotating the square by 90 degree. By rotating the square by 90 degree, that is sigma A into sigma B is independent of how the points are chosen. So here I can say that sigma A into sigma B can be written as sigma 1 into sigma 2. Okay, so this is the condition actually. This is the condition, and let us discuss the condition more precisely. Here we get that first let us see a 2 cross 2 square and the current streamlines and the potential equipotential lines that can be plotted here. So if I just take phi as the electric potential, that will give us the conservative electric field, and psi as the current potential, this is the black square and this is the white square. So if I just take the black square as sigma, it is already given that it is sigma 2, it is already sigma 2, and it is sigma 1, it is sigma 1. So if I got sigma 2 and sigma 1, here the current streamline potential is 0, and here the current streamline potential is I. So if I just take a point A on whether it be the white square or whether it be the black square, I can just define. I will tell you later that why these lines are curved actually. Here we should first see that if I choose a point A and after a distance of delta L, an equipotential line of phi plus d phi or delta phi, whatever you get to use, and a delta S and thickness of delta S, they are orthogonal to each other. First, let me tell that these two lines are orthogonal to each other. So phi are the equipotential line. Phi is the equipotential line, that is the voltage potential that gives us the conservative electric field. Now psi is the total current that flows between the current streamline, any one current streamline that we choose, and the left edge of the plate, the left edge of the plate. So here we can say that E and J are perpendicular to the equipotential lines, and also the current streamlines are also perpendicular to the equipotential surface streamlines. So let us discuss it in a more detailed manner. So here I got this, and it is delta S, this is delta L. Now from this figure I am going to derive some important results that we will be using here. So so in the vicinity of the point A that we choose here actually, so if I see the point A, in the vicinity of that point I chose a equipotential line, and I also choose a current streamline that is perpendicular to the equipotential line, two current streamlines, one at psi and one at psi plus delta psi. Okay, so let us see. In the vicinity of a point A, the field should be written as delta phi by delta L. That is the conservative electric field that can be written with the help of electric potential. Okay, so this potential gives us, according the potential varies across this line from 0 to phi, 0 to v, 0 to v. So we will take electric field as phi and delta L. In the direction of increasing potential, electric field decreases. We have to keep that fact in our mind too. And so here if I write the local current density at A, it can be written as sigma A into delta phi by delta L. Sigma A into delta phi by delta L. Now delta psi is the change in current potential, and using the definition of the current potential we can write it as the current density that is passing through the T delta S area. The current density that is passing through here is called the current potential. So I already told you that what is the current potential. The definition of the current potential was the total current that flows between one current streamline and the left hand edge of the plate. So psi, you can take it as current, not actually potential of something. It can be taken as current streamline. Okay, current streamline. So here the total amount of current that will pass through here can be written as delta psi upon delta s as t sigma t sigma a t sigma delta phi by delta L delta psi by delta s. Okay, so if I rotate by 90 degree this square, here if I rotate this square by 90 degree, that is in the anti-clockwise direction like this. If I rotate it like this in 90-degree direction, this will come here, this will come here, this will come there, and this will go downwards. Okay, so if I just rotate it by 90 degree, uh, I get this what to say this arrangement actually. This arrangement I get, and since I rotated everything here, phi is equal to v. phi is equal to V, psi is equal to 0, psi is equal to I on the upper side. Now here psi increases in this direction, the current potential, and the voltage potential increases in this direction. So if I just choose a point A and again write delta L, delta S, each and everything accordingly, delta L in the direction of increasing phi, delta S in the direction of increasing psi, that all things I write. And now I just use scaling arguments, and I choose a point B on the square, on the black square in the original figure. In the original figure. Now what are these primed variables? Primed variables are the scaled up variables, actually I should say scaled up variables. So if I just take this figure and choose a point here, actually, like that, the inverse of this point, I just chose a point here. uh, in this figure I just chose a point here, and here I write it as delta S dash, but in our original figure delta S was somewhere here and delta L was somewhere here, and here in our this figure we got delta L dash here, and delta S here. So in the direction of increasing phi, we should get delta L, but here we are getting delta S. So we should say that delta L dash is equal to delta S and delta S dash is equal to delta L. From the original figure, I take all these points from this original figure. You can see delta S. Now in that figure, we got delta S here and delta L here, delta S dash here and delta L dash there. So we get all this equation, and in this figure I just write delta L dash is equal to delta S. These two figures I am just comparing them, rotated figure, just comparing with the rotating figure. So with the rotating figure I can get, uh, just compare this figure with this, actually. Let us see. I'm just comparing the two figures, you just compare them, this figure on the right and this figure on the left, this figure to this figure. Here delta S is equal to delta L dash and delta S is equal to delta S dash is equal to delta L. Just compare these two figures. That's why I have drawn it side by side, so that when here phi is equal to V, psi is equal to I. So when phi is equal to V, psi is equal to I. We are just comparing the rotated figure with the figure in our concern, that is the point B on the black square and point A on the white square. We are just comparing the two things. The conductivity will be different, but each and everything other thing can be just written here. So when the potential is V, when phi is V, psi is I. When phi is V, psi is I. So psi dash, this is psi dash, psi dash is I. When phi is V, psi dash is I. So when phi is V, we put V here, and this gets cancelled. So these are the scaled up factors that will give us the correct answers. This means that I have taken the correct scaled up factor. So again we get phi dash is equal to V by I psi, because when psi is equal to I, phi dash will be equal to V. Phi dash will be equal to V. Just compare it here. When psi is equal to I, phi dash is equal to V. Phi dash is equal to V. Just compare the rotated figure. This is the rotated figure, and this is the original figure but with scaled up terms. Original figure with scaled up terms. Okay. So here we get phi dash max is equal to V and psi dash max is equal to I. Now here the point B is at the location at the rotation of A. Point B is at the location. Point B as is at the location of the rotation of A. So that is the thing we are comparing. The two diagrams side by side. We have compared the two diagrams side by side. First we rotated it. We got the location of the rotated point A. Then we just compared it with the scaled up figure, that where the conductivity is at B. So this is the original figure. In the original figure we took a figure just like this, a point B on the black square, and in the original figure you can see, in the original figure we got the black point here. So we got the black point here, A was here and B is somewhere here, and A rotated is also here, but here the white square has came in that figure. I hope you all understand. This is quite a messy thing to understand, actually. So B is bound to be on different squares, so we get sigma B is equal to sigma 1 and sigma 2. Now if I just conclude from the above relation that we got here, that T sigma A, that is the local density, the local charge density, can be related with the potential and the current density as T sigma A delta phi by delta L is equal to delta psi by delta S. That relation, if I use here in this figure, the scaled up figure, if I use the same relation for B, for point B in the scaled up figure, I get to know that T sigma B can be written as delta phi dash upon delta L dash, and it can be written as delta psi dash upon delta S dash. Now from the scaled up terms, if I just take the differential of d psi dash, suppose if I take delta psi dash, it can be written as I by V, I by V delta phi dash, I by V delta phi dash, and if I just do divide it by delta S dash must be equal to delta L. Now that is the thing that I am going to do here. T sigma B is T sigma B into delta phi dash upon delta L dash can be written as delta psi dash upon delta S dash. Now delta phi dash upon delta L dash can be written from the basic relation that I used above, the scaled up relation delta psi by delta S, and then I can write it as T sigma B delta phi dash upon delta L dash can be written as T sigma B V by I delta psi upon delta S, and from the above relation that we derived above, that is T sigma A into delta phi by delta L, T sigma A delta phi by delta L is also equivalent to the same relation, and from this side of the equation delta psi dash upon delta S dash, that we will get from this term delta psi dash upon delta S dash, delta psi dash upon delta S dash. You will just find the delta psi dash here, so it will be equal to I by V delta phi dash, and delta S dash must be written as L. So delta phi dash is already known to us. So delta phi dash can be also written. So I by V delta phi by delta L can be written as delta psi dash upon delta S from the basic relation that we used above, scaling factors. Now from the scaling factors we can just derive it as I by V delta psi by delta L, and delta psi by delta L will get cancelled. So I by V delta phi by delta L, I have just done it here, how it came I just derived it here. You can just copy it. So here it can be written as I by V T square sigma A sigma B V by I delta phi by delta S. From this relation we get I square is equal to V square T square sigma A sigma B, and I is equal to VT root sigma A sigma B. So here we can write it is valid for or n cross n charge. Here we already proved it, and A sigma B already know, I didn't written it here. So sigma A sigma B can be written as sigma 1 sigma 2, sigma 1 sigma 2, and we get the same relation. So n cross n is valid if 90-degree rotation takes place. 90-degree rotation takes place because n is even, and when n is even, 90-degree rotation will surely give us a color change, and color change means the law is valid only when the color changes. For odd it will not be valid, and the result, that is sigma 1 into sigma 2, will not be symmetric actually. So if we take sigma 2 is 2 sigma 1, that is for the black square the 2 sigma 1, and we can consider refraction. The curved lines, the lines are curved because I am considering refraction of streamlines, refraction of current streamlines at the boundary or the interfaces. So here you can just see the diagram. It is the black square is sigma 2, this is sigma 2, and this is sigma 1. So here it is psi is equal to 0, current potential is equal to 0, and all the hard lines or the continuous lines are the current potential, and the dashed lines are equipotential lines. So I hope you enjoyed the solution. This was a quite difficult problem to handle in the exam time. We just use the rotating concept and the scaling factor concept to get our answer. So this law is very important to us to consider for considering this type of problems. We must know this law, uh, and that the number of n cross n squares should be even, because even squares give rotation, and then after the rotation the color changes, and if the color didn't change after rotation, any pair of such point A and B cannot be formed. So I hope you all like the solution. Thanks.